Okay, so in this video we're going to show how to use the NanoDrop One. This is an instrument that can be used to measure absorbance of different materials, DNA or protein. What we're going to do is DNA today. So I've got some DNA that genomic DNA I've purified from packet cells exposed to different UV light sources and purified with the GeneJet column. So what I need to do now is figure out the concentration of these DNA samples so I know how much to use for the next step. Okay. So first thing you want to do is you want to make sure your cells are all, or your DNA samples are thawed out. If they were frozen, the thing you can do is make sure everything's mixed up nicely, just to make sure it's a nice homogeneous solution of DNA. Okay. And then what we're going to do is start reading the sample. So this is the NanoDrop One. Usually it's on in this format with the arm down. When you're ready to use it, it'll say please clean the sample area. So what we'll do is we'll grab a chem wipe here, get it wet with some water, and just wipe down both this top little thing there and the bottom part down there. That's where essentially we're going to load the samples right here, close the arm, and that's going to create a little column of liquid of DNA that can then shine light through to measure absorbance. Okay, so once we're done, put that down, clean the arm, or put the arm down, and now again, we're doing double-stranded DNA is what we're quantifying today. So you can do different things, RNA, protein, whatever you want to do. We're doing double-stranded DNA. It's going to say, it's going to do this instrument self-test. Hopefully this shouldn't be a problem. Okay, so now it says clean both pedestals and load blank. Again, we already cleaned it, so we don't need to do it again. So I'm going to take, repeat, 2.5 pipette works well. And 1 to 2 microliters is what we're going to need to pipette. I'm going to do 1.5 microliters today. And the first thing is we need to load a blank. So the blank is whatever the DNA, your samples are resuspended in or eluted in. So again, we use the solution buffer, or at least what I did yesterday was use the solution buffer with a GeneJet kit. And so what I'm going to do is take 1.5 microliters of that, open up that, and basically just load the sample right on that bottom pedestal there. And so it's hard to see, but there's a little bit of water there, or a little bit of the dilution buffer. And now we're going to lower the arm to measure the blank. And then, again, we're going to, between every step, it's going to say clean both pedestals and load sample. So in this case, all we could do is basically just soak up the DNA, take a chem wipe and soak it up. And I'm going to take my first sample, do essentially just what I did with the blank, take 1.5 microliters, pipette it right there, and put the arm down. Okay, so what it's going to give you is a bunch of information. I typically will just write things down on a piece of paper to record the information I need. You can actually export the data from the instrument as well to a file that you can upload or open in Excel. It gives you several numbers. One is first if you look at the graph, that's the absorption spectrum. So again, it's basically exposed the sample to different wavelengths of light, UV light, and measure the amount of, or then it measures the absorbance, how much of the DNA was, or how much of the light was blocked by the sample. And again, the peak is about 260, so again, DNA absorbs very well at that range. So then what it does, it gives you some other information. One, it gives you the concentration. So there's a formula you can use to basically calculate the concentration based on absorbance. So it's 27 nanograms per microliter, so I'm going to write that down. It also shows the A260 to A280 ratio. And so again, nucleic acids absorb very well at 260, proteins absorb well at 280. A good clean sample is going to have an absorbance, or an A260 to A280 ratio of 1.8 to 2 or so. It also looks at the A260 to 230 ratio, There's other contaminants sometimes that absorb well at 230, and so we have an appropriate number there. If some of these numbers are high or low, that'll give you an error message. And so we'll run through the samples here and see if we see anything with that. Hopefully we have nice clean DNA. This is not a problem. And so when we're ready, we'll load the next sample. Just take a Kim wipe, soak it up. We'll go to the next sample. Again, sometimes it can be useful to use two hands to kind of guide your finger to pipette. It's hard to probably see maybe on this camera, but there's a little bit of 1.5 microliters of DNA on that thing right there. Okay. So this did give a little bit of information here that could be relevant. So that little information thing that pops up there. So we actually click on that. It's basically going to tell us that the A260-230 ratio is above the accepted limit. So it should be between 2 and 2.2. And again, that was about 3.02. And that, it could be because there's other, it gives you some possible causes. It could be something's dirty. So one thing we could do is potentially just run through another samples and see if this happens with other samples. We could clear it again. We can see if that makes a big difference. How about we do that? So we're just gonna take some water, and clear it. We'll run the sample again. Some people like to measure all of their samples, 2-3 times and calculate an average. I tend to, if I get like a message like this, or one of the samples concentrations is way off compared to the others, then I may measure it again. So here we get 31.5. Otherwise the numbers didn't change too much. The A260-230 ratio is a little bit lower, and it's not giving us an error message. So potentially just cleaning the pedestals enough to avoid some of that problem. Close it gently. You don't want to slam it down. You don't want to break anything. This is, I think, is an $8,000 instrument. So again, we're still getting that error message. We'll try to measure it again, see if we can get rid of that. It may not be that big of a problem. It affects essentially the purity of the sample. And depending on what you're doing, it may or may not be an issue. So like what I'm gonna do with this DNA is do a dot plot. It really is not gonna make a big difference if the sample is maybe a little bit dirty. And again, there could be other things in the wash buffers or in the lysis buffer that could kind of carry over. Yeah. So again, the numbers did not change too much there. We got 26.2, 24.2. So that's kind of have we can average it and get 25.2 if you want. It's not going to make that big of a difference probably. The key thing is if something's really off, or then I might be really double checking the sample. There is some limitations to how accurate this instrument is. If it's under, I believe, 10 nanograms per microliter, it's not very accurate. So the DNA has to be of at least a certain concentration for the instrument to be able to reliably detect and measure protein concentration. Okay, so like this next one, concentration's a little bit lower, but again, all the ratios are fine. So again, I got 12 samples. I'm not going to record me measuring all of them. That's essentially how we use the NanoDrop One to calculate DNA concentration. And again, this is useful or key for maybe downstream applications where you're going to, in this case, I'm going to do a dot plot. I need to load 100 nanograms per spot on a dot plot. So I need to know the concentration of DNA in order to do that.